Happy Thursday. One more class until spring break. We're going to finish up direction drills. I think I have 2 problems left to cover. Then we're going to start multiple integration. This is 6. So recall. First, we're going to need the gradient. Right, so what is our gradient?
The 2x negative 4y equals z.
Let's actually evaluate that at the point. Do negative 4, negative 8. Or we can factor out the 2. Next, we need a direction vector. Specifically, a unit direction vector. We have a direction vector. It's not unit. Let's make it unit. Right, 1 over the length, which is root 6. Right. Then derivative of f in the direction of u at the point is our gradient dotted with our unit vector. Two minus 2 is 0. Eight over root 6. Same function, same point. Gonna find the direction of maximum increase and direction of minimum increase. And then we'll find the actual maximum minimum rates of change. In general, how do you determine the direction of maximum increase? So what would the direction of maximum increase of a function be? Oh dear. This actually does not require optimization. It's the gradient. We calculate the gradient. There's your direction of maximum increase. Direction of minimum increase. What do we think? Just the opposite direction. Maximum rate of change. What do we think?
Negative.
That's a P. It's the magnitude of the gradient. So we're gonna get what? 4, 16 is 20, 64 is 84. The square root of 84, which is 2 root 21. Do you have a question?
Oh, no, I was gonna.
What do we think for the minimum rate of change?
-2 square root of 21.
It's just the negative of the magnitude. Questions on the directional derivative. Moving on to multiple integration. This is where the course now gets really fun. Starting with double, right? So remember when we were integrating in Calc 1, it was single variate, and you integrated over an interval, right? Well, you want to integrate a two-variate function. That's now a double integral. You have to integrate with respect to each independent variable. Your domain of integration is no longer an interval. It is now a region in the plane. Right, it's a two-dimensional domain. Three variant would be a triple integral. And your domain of integration is now a region in space. Four variant would be a quad integral, let's call it. Quadruple integral. Your domain of integration would be a region in hyperspace. A four-dimensional region, and so on and so forth. Which makes string theory really interesting. Because string theory deals with, what is it, 10 variant functions? Time and 9 spatial dimensions. Oh joy. If you were to integrate over some interval dx, what was the result? What was the geometric result? I'm going to call it, I'm just going to call it ds. I didn't discuss this in Calc 1 or 2. That's not good. The length of the, I'm sorry, it's the length of the interval. Right, integrate 0 to 10 dx. It's just 10, isn't it? That's the length of the interval 0 to 10. Integrate 5 to 100 dx. You get 100 minus 5. Well, that's the length of the interval. It's 95. I'm going to be using that fact a lot. You integrated a function over an interval. What was the geometric result? Now this I know is covered in Calc 1.
Area under the curve.
Not technically area. You're close with area. You're missing something. It's assigned area. Gives you positive if the region is above the x-axis, gives you negative if the region is below the x-axis. Right, and then if you happen to have equal areas above and below, the entire integral would be 0 because the signed areas cancel each other out. If you wanted specifically just area, you'd have to do the absolute value of f. What do we think if we just integrate over a domain D, two-dimensional domain D, dA, what's the result going to be? That's a script D. Acceleration, not acceleration. Single integral gave you length. Double area, the double integral is going to give you the area of the region. Call it A of D. By the way, that now means that we don't need to do a single integral to calculate area.
When you say area of the region, what is the difference between the area we were finding before? It's just dimension, right? Like you were saying earlier.
Well, what do you mean area before?
Like we were saying, the second one, that's signed area.
Right.
I understand like what you mean by signed, but what's the difference between that area and then area of the region?
So signed area depends on where you're located with respect to the x-axis. This is just area, right? So square, length times width.
Okay.
So that is going to be always positive. Then what are we going to get if we take a double integral of a function? Again, not technically volume, just like it wasn't technically area. It's assigned to volume. Positive if it's above the xy plane, negative if it's below the xy plane. Learn how to spell. There you go. If you wanted just straight up volume, you just do the double integral of the absolute value of the function. And that would give you volume. We'll look at the triple integral analogs when we actually study triple integrals. But you should easily be able to guess what they're going to be. Uh-oh, I think I skipped the sheet. Did. That's okay. So before we start looking at setting up a double integral, we take a look at what's known as iterated integrals, because all double integrals is going to be set up as an iterated integral. So here's how iterated integrals are read. Start with the innermost and work your way out. So first we're going to integrate from x squared to x with respect to y. Well, that is just a length. Well, so that inner integral is going to evaluate out to x minus x squared. Then we go 0 to 1 of x minus x squared with respect to x. Well, that's calc 1. I'm not even going to write it out. X squared over 2 from 0 to 1 is a half. X cubed over 3 from 0 to 1 is a third. So a half minus a third. 1/6. So that iterated integral is a sixth.
We're using the first one we talked about up there.
Yeah, it's just going to wind up being like right top minus bottom. So first we're integrating from y to 3y of x plus y with respect to x. Antiderivative of x with respect to x. That's the derivative. We want the antiderivative. Antiderivative of y with respect to x. xyx. Or xy. Then just evaluate that from y to 3y. Nine y squared over 2 minus y squared over 2 is 4y squared. Then we get 3y times y is y squared minus y times y squared. So we have 3y squared, 3y squared minus y squared plus 2y squared. X squared over 2 from 3y to y, or from y to 3y, right? 9y squared over 2, and then minus y squared over 2. So I evaluate each piece individually over the interval. So that'll be what? 2y cubed? Evaluate from 1 to 2. So 16 minus 2, 14. Two y cubed. Because that's 6 out in front. Need to integrate first with respect to y. There's no y in the integrand, is there? No, right? That makes the first integral extremely simple. It's gonna be x times the difference, right? X times that length. So x squared minus x squared, that's nice. That's 0. We're gonna be left with x plus 2. That's what I actually blow right out. X cubed over 3 plus x squared is the antiderivative. And I get 8/3 minus negative 1/3. It's 3. 4 minus 1. Is that integral 6? Right. Notice with iterated integrals, you evaluate them the same way that you would do in Calc 1, Calc 2, except since it's iterated, you're going to have multiple times you have to integrate. That means all of your techniques from Calc 1 and Calc 2 are valid. You just may have to use them more than once. Or you may wind up with a mixture, a whole bunch of them. Or you can just do what I do when I set up triple integrals, then I just probably plug it into a CAS. Because it's the setup that's the most difficult part. Iterated integrals, you're not going to be allowed to use a calculator for the most part, right? So if the problem's set up like this, I actually want you to do it by hand. Versus when we start looking at actual integrals, where the setup is the challenging part. Then you can just set it up and then plug it into a calculator and show me what you get. What do we need to integrate with respect to first? What is it? Rho, right? 0 to pi. Gonna pull out the 1/2. And I'm not even gonna bother because it's rho squared. Just gonna wind up being cosine squared. How would you evaluate that integral?
Cosine squared theta to 1 minus sine squared theta.
Then you're gonna have sine minus sine cubed. While valid, what's the antiderivative of sine cubed? There's an easier way.
Think, cosine theta equal U.
Yep. You sub. So you get negative a third cosine cubed theta, then just times that 1/2. Cosine of pi. Cubed is -1. Cosine of 0. Cubed is 1. So cosine cubed from 0 to pi is -2. Integral's a third. Antiderivative rho cubed is rho to the 4th over 4. Factor out of 16. Just to make life a little bit easier. Right, so remember integrals are linear. Flip this into 2. The integral of 1 is just the length of pi over 2 to, or 0 to pi over 2, which is pi over 2. Times 4 is 2 pi, so that's where that -2 pi came from. And then just factor out the 16. You get 64 integral of cosine to the fourth. How should we go about evaluating cosine to the fourth? There would be two accepted ways to do it. One is simpler. There's a Calc 1 method and there's a Calc 2 method. Calc 2 method is integration by parts. Should have derived the cosine reduction formula in Calc 2 to integrate cosine to the n. That is derived using integration by parts. So you can use that. Or the cosine reduction identity. Which is the easier method. Remember the cosine reduction identity? Cosine squared of theta, 1 plus cosine 2 theta all over 2. Oh, wait, that should not be... Sorry, that should be squared out there. Which means, actually, I'm dividing 4. Because the half has to be squared. And that poor minus 2 pi is just floating there, hoping not to be forgotten. Now we have this cosine squared of 2 theta to deal with. Well, that would just be a half plus a half cosine 4 theta. Right, so 3 halves plus 2 cosine 2 theta plus a half cosine 4 theta. A very useful property of integration that is often forgotten. If you integrate a periodic function over a multiple of its period, it's 0. Right? Because what does it mean to be periodic? So for instance, cosine is 2 pi periodic, right? That means cosine of 0 and cosine of 2 pi are the same. Specifically, cosine of theta and cosine of theta plus 2 pi are identical. That's true of all periodic functions, right? If it's n periodic, f of a and f of a plus n are identical. That is why the integral is 0. What is the period of cosine of 4 theta? Put it here. Well, you know cosine is 2 pi. So cosine of 2 theta be. You did the wrong operation. It's pi. You divide by the coefficient. 2 pi over 2. So what's the period of cosine of 4 theta? Be 2 pi over 4, which is pi over 2. That last term is going to integrate out to 0.
You go over there.
Period of cosine of 4 theta. It's 2 pi over 2. Or 2 pi over 4. Which is pi over 2. We're integrating over one full period of it, so it's automatically 0. That is also a property that I'm going to be using a lot. That means there's actually 2 terms we have to worry about. Bummer that wasn't 0 to 2 pi. Because then I could have eliminated that cosine of 2 theta as well. Whatever. 0 to pi, I think I could have eliminated. If it was 0 to pi, I could have eliminated both terms. This cosine squared of 2 theta. It's 1/2 plus 1/2 cosine of 4 theta. Oh, that is very nice. Oops. Yeah, that 2 pi's crying because I forgot it. It was only a matter of time. Surprised it lasted that long. Sine of pi. Sine of 0. That sine term just goes to 0. That's nice. So we're left with 3 pi over 4 times 16 is 12 pi. That integral evaluates out to 10 pi. Questions on iterated integrals?